Hello everyone and welcome to today's webinar tutorial about SeeSAR 9. As I've seen that most of the people are rather in the early stages of SeeSAR experience level, I will start at the beginning. I still hope that the frequent and professional users find some of the new gems inside it. So I will start with a new project today, and you see already, if you've seen SeeSAR before, that it looks a little bit different now, quite prominent here on the top middle bit is the mode switch button. You start from the protein mode, and when hovering over, you get a selection to choose to go to those other modes. For example, the docking mode. You see by default, all those modes are empty. So for those who have used SeeSAR 8 or other versions before, there are less cross dependencies. You can use all modes individually and don't have to rely on results from other modes. We start from the protein mode. You see here those data table switches a little bit. There's always the respective data which you have in the modes. On the top left, you have the classical protein saving and loading. The second button on the top left always allows you to bring data into that mode. I will do this now, and the first field here says download a PDB, so I can type 2xjx and press enter, and what happens is that the protein is loaded from the PDB directly. What's new as well is that we have a little protein definition dialog here, which lists all the heteroatoms which are in the PDB file. This is quite new. In this case, it's a little bit boring because we only have that one ligand here. But imagine you have buffers and cofactors and so on. You can directly decide if you want them to be part of the protein, like for example, a cofactor that shall always be around but not considered as a ligand. Or you can consider them as the ligands you want to work with, which I will do with this one. If you find things like buffers and, let's say, glycerol for the crystallography or PEG, then you can remove it here directly. And what's new as well are those green action buttons. So press the define button, and SeeSAR will prepare your protein. And the ligand is extracted now and here in the table. If I click on that ligand, it's here in the 2D window. We've seen quite often that people who don't see anything might have the problem that those tables overlay. That is unfortunately dependent on the Windows or display settings usually. So if you don't find your table entries, look at those buttons and remove them a little bit. Equally, you can drag the width of the table, the sequence view as well. The sequence view shows you the parts of the protein. If you see, I hover over the sequence, and in 3D, in those pink sticks appear the individual amino acids. And you see as well, you have the protein as the blue ribbon, and you have the ligand with the coronas around. You know this from before. If I press the space button on my keyboard, SeeSAR zooms in automatically. This is the usual view you know from before. And for those who have not much experience with SeeSAR, for each atom, for each molecule in the table, we have an estimated affinity here. This is this arrow bar. It's not a slider, so if you pull it down, your molecule won't get a better affinity. You have to earn this. It's just the affinity we calculate. And to explain you further on where this affinity is coming from, we have the coronas around each atom. They show you the individual contribution of each atom to the binding affinity. Means like when you have a green sphere, this is good for your binding affinity. If you have a red sphere, then this is bad for binding affinity. And the bigger the sphere is, the stronger is the contribution. If we do have any people in here that are red-green blind, please go to the appearance button here on the top right and select the blue-red mode where the blue coronas correlate to the good affinity and the red are still the bad affinity. So I will switch it back because most people are not colorblind. It's just quite helpful for those who are. Equally, we can switch the theme now that we're here in the display settings. I will put it maybe on the bright mode here, which is quite good for presentations and when you work on a projector, then people normally see it much better. You can change the layout here if this is your preferred style to have everything on the bottom. You can undock them and move them to a second screen if you want, or bring them back to the original layout. Equally, the background color, I will make it a little bit lighter for this presentation, hoping that this gives you a better view on what I'm doing here. Okay. All the buttons here on the top right are independent from the mode I am in. On the top left will appear buttons that are just precisely for the modes we are working in. So first thing to do is we've seen the molecule, we've seen the protein around, but this is just looking so far. The first thing we want to do is define the binding site we want to work with. Equally, again, here I chose a quite simple case where we have only one ligand in the protein, but imagine you would have several chains, then you might want, or then you have to select the one you want to work with to make this decision once for the computer. Okay, so to do so, we click on the row menu here on the front of the table entry of the ligand and add this molecule to the binding site mode. You see now here by this indicator on the top, it's green colored now and it says binding site, so I'm a different mode now. And I can define my binding site here. I see my molecule in 3D. I can equally click on this and the amino acids in the vicinity are now selected. They are those pink sticks and the surface that belongs to that binding site is shown. A new feature is that you can deselect amino acids here. Let's say this phenylalanine here on the bottom is not of interest for me, or this acid here, then I can deselect them. I can all bring them back by saying select the surrounding residues in the row menu of the table here. If this is not the binding site I might want to work with, I can reset my binding site definition and let the computer search for unoccupied or hidden pockets. It finds, of course, the one back where my ligand is inside, but I see as well there are two more here on the back side of the protein. If I look at the table, I can see that the yellow pocket consists of 14 amino acids, the green one as well of 14, the pink one, that's the one around the ligand, consists of 34. Just so you know how to find the empty pocket, I can hide them again by toggling that button. So for now, I will select the amino acids around the crystallized ligand, and I will confirm my setting with this green action button here on the top. Okay, my binding site is set. You see equally that here on the sequence view, some are now highlighted in blue. Those are the ones which are part of the binding site. The other ones are in gray because they're not displayed here. Okay, let's go back to the proteins mode. And I see now my ligand here surrounded by the amino acids, which are part of the binding site I want to work with. And the next thing to do would be to analyze the binding site and the binding mode, especially a little bit more, because those coronas are already an indicator where you have strong binding motifs and which parts of the molecule do not contribute. For example, your piperazine moiety here, which is sticking out to the solvent and does not have any coronas, means like it's not contributing to the binding energy at all. But to find out a little bit more about the binding motifs, I go here to the Label and Measure button and activate me the label function. You see now what is activated is always highlighted by a blue bar under the button. And you see my mouse changed as well a little bit. There's the little label next to my mouse. And when I click now, for example, here on the methyl group that sticks deep inside the binding pocket, I can see this brings me 8.2 kilojoule per mole, and we always discriminate between a desolvation energy and an interaction energy that I gain. You see here we have as well a ligand and a receptor column. The interaction line is 0, means like there are no hydrogen bonds around this area, but the desolvation line is quite interesting. So we have the ligand bringing energy and the receptor. For the ligand, this makes of course sense. I can see that with my eye that I have a methyl group deeply buried inside the binding site. This is of course a favorable mode of binding, but for the receptor I don't quite see it right now. So I can click on that eye here. I can, by the way, remove that label and pull it to the side by just holding it. And with those pink interaction lines, I can see now the points of the binding site that are covered by this methyl group. And I see I'm here in a very hydrophobic environment. So this makes, of course, sense that the receptor is quite happy to have another fatty atom around it and not like water as it was before the binding process. Okay, like this, I can go through all my molecule and find out where are the interaction patterns and what might be interesting to modify, and so on and so on. This is so far looking. This is, of course, good for understanding the binding mode, but the interesting part comes, of course, when we start to edit. Just before editing, I'd like to clean up my view a little bit. You saw this already. Some of the waters are in my way and the ribbon is a little bit in my way. So what I'm going to do is down here in the sequence view, I have control over all the individual parts of the molecule, like the residues or the ligands, the metals, the waters, and the cartoon. So I've clicked on the cartoon here, and those are all buttons, yeah, so you can deselect it here or here. If you have several chains, then you can select individual chains. I will remove the secondary structure by clicking on this. Again, if you mouse over, it will be highlighted. So if you leave your mouse here, you will always think you haven't deactivated it yet, but just remove your mouse a little bit to the side and you will see that the structure is gone. I will do the same with the waters. For the waters, I will put here the switch on just the binding side waters and will hide them now. And what I can do here is just add the interacting compounds, which are none at the moment. Okay, so I've cleaned up my view a little bit. The next thing to do was finding out how my binding affinity will change upon modifications on the ligand. To do so, I take this ligand and copy it over to the molecule editor. You've seen now that here new buttons have appeared, which is adding atoms, changing element types. You can change charges, you can change bond types from single to triple. You can rotate bonds around, but at the moment most of the real action buttons are grayed out. This is because I haven't done any selection so far. In SeeSAR you always have the mantra kind of first select, then act. So what I have to do is to select something of my molecule which I want to modify. You see now that all the coronas are gone, and instead of that I have the hydrogens as those white bubbles here attached to the molecule. So what I would do is, for example, selecting here this hydrogen, which is deeply buried inside the binding site, and try to make a tert butyl group of this. So I select this and go here to the change element button and click on a carbon. So you see a methyl group was attached, and it has already the standard bond length and angle, but the whole molecule is not fully minimized yet. To do so, I save the edited molecule to the table. Whilst this is happening, the molecule is optimized and the height coronas are calculated. If I click on that entry on the table, I see now all the coronas have appeared, and you see that I've added another green sphere here. To compare this to the original one, this one lost its affinity by copying it out of the protein. So what I do is click on the row menu and calculate the estimated affinity again, so I can compare if I made a good change or not. Aha, so you see I've added a green sphere, but actually I've got a little bit worse in affinity. So why is this like this? If I compare, click on the second one again, I see that here on the back side I'm slowly growing a red corona. So I must have dragged the molecule a little bit more outside of the binding pocket because I was obviously pushing it a little bit out. If I want to compare this, I go back to the starting point, click on the row menu, and toggle the starting point as a reference. It's now in this purple color. If you're not a big fan of purple, just click on this here and select, I don't know, cyan if you like this more. And click again on the molecule you've edited, and now you see how you've slightly switched the position over from your starting point. So you see now here the carbonyl is a little bit pushed away from the perfect H-bond geometry. This is obviously why we lost a little bit of binding energy here. So what we do is resume the editing, and let's say we've seen before that the piperazine group doesn't make any difference. So what I'm going to do is I select this here. I can either select in 2D or 3D, both is possible. This is synchronized, so if I deselect it here, it will be deselected there. And you see as well, I can toggle over it in the 2D and it will appear in the 3D as well. So I've selected this now, and what I'm going to do is I take here the waste bin and just remove this bit of the molecule, bring it back to the table again. And now I see, oh, I've basically lost not much binding energy, but I've maintained the affinity. This is of course interesting if you want to change the physicochemical parameters of your molecule, and you can find more out about it if you change the number of visible columns here. If you click on that button on the top right of the table, you can get more columns here, like let's say the molecular weight, which I've of course drastically changed here. And we collaborate with a company in the UK which is called Optibrium. They're pretty good in predicting ADME parameters, and from them you can get information like, let's say, log P and log D or hERG estimated affinity. If I look at this, I see, of course, I've not changed much my binding affinity, but I've of course changed, for example, log D drastically. Equally, I've lowered the hERG PIC50, so you see you can do some good multi-parameter optimizations from here whilst you're designing new compounds, find out a little bit more about your ADME properties and the physicochemical changes you're making to your molecule here. So keep an eye on that if you know what your targeted area is. If you try to get into the brain, if you try to get into the human blood, or if you try to get into a bacteria, you might be very interested in looking at the log D or the TPSA. So you can have a look on those parameters here as well in the table. I make this a little bit smaller so I have more interaction space in the 3D here. I'm a little bit annoyed by the reference here, so I go on the row menu and say, do not show me this as a reference anymore. And you have seen how to make changes. Just whilst the coronas are there, we cannot display the hydrogens. This is why the editing menu is locked here on the top. This is why I press the resume button, then my hydrogens are back, and I can make further modifications. You can equally make little rings by pulling out a bond here out of the carbon and just snap it onto another carbon, and you see now I made a little cycle here in the bottom, and again I score it and see what happens. So like this you can playful edit around and make some new suggestions on your molecules. So far so good. This is of course very helpful as long as you have a crystal structure to start from. Lots of people ask us, how do I bring in my own molecules? And for this I have two cases. One case is where your molecules are docked already by any other program. Then you just go to the analyzer mode and go here on the second button and say load molecules. I will do so and have here a set of ligands that are already docked into that binding site. If you look at them, you will see here they appear in the 3D, but they don't have the coronas yet. So what I do is select all of them with the checkboxes here on the top front of the row, go to the calculator and say calculate me the estimated affinity. So height is now calculated for all of those molecules. And you see I have a mixed set here of molecules. Some are a bit more active, some are a little less active. All have those beta-radicylic acid motif binding on the bottom. So this is the way you bring in your molecules. By the way, if they have weird names, then you just double click on this and rename this as my best or whatever your name is, and just confirm it with the enter button, no, not buttons, key on your keyboard, sorry. You see here there are some columns about the torsion and the clashes. Torsions are of course very interesting. If a torsion angle is maybe unlikely, then you might not want to trust your docking results. On the visualization button here on the top right, I can toggle on the torsion coloring. You see now those torsion are color coded from green to red. And again, going to the label function, I can get a label and color those torsions. And then you see statistics, which is derived from the CSD, where you can see how frequently torsions occur. This is maybe a little bit bad to see, so I go back to the appearance window and increase the label size so you can better see this on your screen. I hope this helps you. You see here, this is a quite low distribution, let's say, so there are lots of likely angles which are indicated by the green areas here, but equally you see we're here in the complete minimum of what happens. So this obviously occurs only in about 26% of the cases. Means like this is a very weird torsion angle. You might not want to believe this. So have a look at those things and be careful what your docking results are. Let's say we like this molecule, but we just do not trust the docking mode. So we can take this molecule, we can either check all. I will uncheck all and I will just take this one over to the docking mode. Taking molecules over to different modes can either be done via the row menu here by clicking on it and adding it to a different mode. As you saw before, I can check those boxes at the beginning of the row and transfer the molecules over with the button here on the top. If you want to do actions on several of those molecules, this is of course the way. If you transfer only one, you can take the shortcut via the row menu. I take now the long way to show you how to bring it over to the docking mode this way. So I have now one molecule in my docking library. This is a little bit hard to see here because it's hidden a little bit. And what I do now is setting some parameters. Let's say I want to have about 20, 30 poses, whatever you like. We say 20 now. And I can generate the poses then. I can set pharmacophores if I know some key interaction features I have to maintain. But for now, I'm just going to let me surprise by the algorithm. For you who work together with computational chemists a lot, here the button exports you the docking settings from SeeSAR. So if you want to prepare your binding site inside SeeSAR and have the nice visualization before you start a high throughput docking, you can do this all in SeeSAR and export your setting from there to use it on a command line tool or bring it to any cluster if you want to. Okay, my molecule has been docked now. You see here all the solutions. And what I'm going to do next is select all of them and calculate the affinity, which hasn't been done by default. This is something I trigger manually, because if you make a very long list, you might want to have a look at compounds binding modes first and not select them for all of them. Calculate them for all of them. And you see this is quite fast, so 20 poses, affinity is calculated pretty quickly. I will calculate again the torsion quality and the clashes, which I find very important. And then you can directly see here you have those traffic light notifications in the table if they are having green torsions, orange torsions. Luckily no red torsions, but we see here we have some intramolecular clashes, and to visualize them, I go back to the visualization button here on the top right and start the clashes as well. And so we see here those atoms come pretty close to each other, so they have a red arrow between them. Red means the van der Waals radii of those two atoms start overlapping by more of 90%. I'm of course a curious person. I want to find out how close are they, so I go to the Label and Measure tab again, get me the distance measurement and start measuring from here to there. 2.83 angstrom, yeah, this is pretty close for 2 carbons. They might not be super happy with that. Can remove this again. So you see you can go through your docking results and see how are my torsions, how are my clashes. Luckily, we don't have any clashes with the binding site here, but this could occur as well. So keep an eye on those as well. We hope you can see them quite nicely with those arrows or here in the table. If you have a lot of docking results and want to analyze them further, we can recommend you to check them all and bring them back to the analyzer mode. And here you have those filters I've showed you before. You can select filters like torsion quality shall not be worse than the green ones. I just want to keep the ones that are green, and apply the filter with the green action button here on top. So you see now I can apply as a second filter. Let's say I don't want anything that has clashes here. I just want the green ones. Apply that again. And now you have a look at those 8 ones that are still of interest for you. So I would say this is quite helpful when you do something like a hit triaging from a big virtual screen and you want to find out what are the trustworthy ones here at all. Am I looking at lots of interesting molecules which have all untrustworthy binding modes? This is of course not helpful for you. So from there on you can select them more. So lots of people like the not so crowded view a little bit better. So here I have lots of hydrogen bonds and interactions, and here I have some amino acids which are not of interest at all. I can of course manually remove them here by finding them in the sequence view and clicking on them and not showing them. But what I can do is clicking on this first button here, which is relying on responsible for all the particular amino acids of the binding site, deselect them all, and then click here the little I, which is just adding the interacting ones again. So I can get a quite cleaned up view around my binding motif here. I can add further if I say, okay, I want to close the gap here a little bit or add 2, 3 more, which are of interest. I don't know, this one, for example, this one. And lots of people ask us, so how do I make a good picture for the publication? I turn them on again because I think it's a little bit nicer like this. Let's say you want to get 2 different views for your publication. Let's say one with a surface around, and we make this transparent. And let's say color like log P, so we see a little better what's behind there. Is there anything good behind or bad behind? I want to remove the clashes because I don't want to have them in my publication picture, just like this. And I can zoom in and out. And here on the utilities button, I can create images. I can either make a screenshot for paper mode, which is good like for having this in any small picture, but if you want to make a poster or something bigger, then you can go here to the poster mode. This is the right button, and set the dot density you need and create the biggest image you ever want. I don't know, let's say shoot, and we make a test image on my screen. And let's go here and find it. Oops, I obviously haven't stored it on my desktop. I'm sorry. Let's look at it later. Equally, you can make a very cleaned up picture. Lots of people say, I don't want to have this all looking like this. So we remove the surface, remove the torsion. We can actually remove the coronas as well if we want to. Remove all the amino acids, just add those of interest. And let's say give a little bit of fog around to give this a depth, or remove it, whatever you want. Just make the background color on white again to have a good contrast here. And like this, you can make pictures just the way you want it. Actually, some people prefer not to have the sticks and balls at all, so we make this a reference and color it by green, I don't know. So then you can make pictures like this, like you're used from having them in PyMol without all the interaction lines. This is possible as well. Equally, some people ask us, how do I color my protein? I like this a lot, so I go to the Proteins tab again. Here you can select the color of the protein as well. So we do something very fancy now. We have all the amino acids in purple. Equally, you can come back with the secondary structure around. This is the way to make pictures of this style, or again, having the ligand in this shape in here again. Or again, moving all the amino acids if you're looking for a picture like this, and again go to the utilities tab and make a shoot of your scene here. So to remove all this, because it looks quite fancy, I would say, I do not show this as a reference again, and I go back to the proteins and remove the color here with a little X on the front. So I have showed you how to edit things. And when the editing was, we have to bring in the coronas again and the things. remove the secondary structure again, but bring my binding site atoms, binding site amino acids back. So I'm back to the view where I was before. Some people always say, this view is a little bit too crowded for me. I don't see this very well. And when I turn on the surface, I don't see what's behind so nicely. I don't like it. For those people, we created the fog, which shows you the unoccupied space around your ligand. And you see when you zoom a little bit closer, there are those little spheres here. And each of that sphere indicates that there is space for at least one fluorine atom around your molecule. So this is not the complementary space which is between the ligand and the surface, it's just the minimum space. So this gives you an indicator where it might make sense to grow your molecule into the direction. And growing the molecule is always a quite difficult task. People need to do this a little bit blindfolded. So let's say resume, we want to target the fog which is here, so I can just go there and add a carbon, and you see this fog is changing on the fly. So when I bring atoms inside, it will move away and give you the new minimal space you have. So you can easily explore your protein surface or the binding site this way. Lots of people tell me I'm running a little bit out of ideas. Yeah? I don't like this too much. I need a little bit more guidance here. So for this, I will create an example where we have only a fragment binder. So I remove this and bring this molecule to the table here. Now this is my new starting point. This has still a quite okay affinity because I maintained the beta-resorcylic acid binding motif here in the bottom of the binding site. So I take this molecule and bring it over to the inspirator. The inspirator is for you when you start running out of ideas, when you are not wanting to try out everything yourself. And one thing we can do from a fragment is select a bond. And use this as a starting point for the growing. Those conic shapes of this little pink bars here have a direction, so the light part will be replaced. Means like in this case, I want to grow out of the binding site here. I put it in this direction and just started growing here. And what happens now is that SeeSAR runs through a database of little fragments to which linkers are attached and starts building them all together with the growing start fragment that I've used here, which you see on the left side. And the protein in this case is a sphere around all that and is a kind of exclusion volume. So there will nothing be surviving that would clash with the protein. And in the next step, the ADME parameters are calculated automatically and the binding affinity is calculated. And hopefully in a few seconds, we will be coming up with some new ideas regarding the exploration of the binding site around this fragment starting point. You see, this is a still quite rapid process. So the general remark here, SeeSAR runs locally on your PC. There is no cluster behind this. There is no cloud which is used for this. This is all on my personal computer here. Nothing hidden behind the scenes. All locally. Okay, now I come back here with lots of new ideas. You see some of them have better scores, some of them have worse scores. This was my starting point. And you see I have here affinities, and if I want to find the ones that are better than my starting point, I can sort this column. All those column headers are for sorting. If I click once on this, I have the ones with the best affinity on top. You see here my starting point is quite low, so I can go up, 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 up and find some good new examples. And the new parts of the molecule here are highlighted by this orange spheres around the bond. And like this, I can click through all the new proposals and look for some that I might find interesting and that I might want as new starting points. Of course, you can repeat the process. Again, here, be careful with the torsion coloring. You see that the torsion was a little bit moved around whilst the growing happened. And yeah, like this, you can browse results and get some new ideas for a fragment growing. Another use case of the inspirator would be the recore functionality. Means like I replace a core in the middle of a big molecule. There's of course here not the best example for this. So I go back to my analyzer mode where I have the molecules that I brought in. They're filtered out at the moment, so I have to remove my filters again and apply that again so they're all gone. The molecules I've brought in and scored are some explorations as well that we found earlier, and you see now the piperazine is not a piperazine anymore, it was modified, and this way it finds interactions here at the further outside of the binding site. But still the middle bit here is not quite interesting, it's not making too many interactions, so this might be a classical starting point to do a recore search. So for doing this, I take the molecule and copy it over to the inspirator mode again. And earlier I've selected only one bond. Now I'm going to select 2 bonds here between those rings and then browse a database of 3D fragments of drugs, which will be hopefully fitting quite nicely in between the bonds that I've cut here to bring in some new molecules. And again, you see this works quite rapidly. I get some new ideas here rather quick. They are now, where are they? Oh, they're a little bit hidden. I sort this by name again. So then they will be at the end of the table. You see some of them just didn't survive the scoring because they were moving around probably too far off or had clashes. But here is a new idea which looks quite nice. If you say you don't like those ideas, you can resume this and say, okay, I select another bond. Let's try to grow a little bit, let's try to replace a little bit more and run the search again. So you can play around here and replace everything that you find worth replacing and generate new ideas out of the data set which is behind this. Let's see if there's something better now. Now I got some better proposals. And equally here is one which has a very good binding affinity. Okay, but this is a quite boring molecule. So you see binding affinity might be nice, but the molecule might still be boring. So leave the computer on and your head as well. Use those just as ideas for you to stimulate your brain and find out what's reasonable and what's not reasonable. Okay. Equally, you can, when you use this for the very first time, those buttons might be grayed out. This is because you haven't set a recore index yet. You can do this here in the settings. Go to the inspirator settings and you can download the recore index for this from our website. If you click that button, you will be prompted there. Just click the very first link here, download this and add this to the mode here, just like I did, pointing it to the download path, set apply and close. Equally, you can use different indices. If you're a subscriber of the CSD, they have an index with their data in there, or we can create customized recore indices from your in-house 3D crystal structure library. If you're interested in this, please contact us. Okay. You can do here fragment merging as well. If you have 2 fragments, you can bring them over together to the inspirator mode, select 2 bonds. As this gets a little bit crowded here, I'm cleaning the inspirator mode to get all the new ideas off. And I go back to the molecule editor. I've created this fragment here. I resume this now and go a little bit back. I don't know, like this, and remove now, no wait, further back, there we go. And now I just remove the other bit of the molecule. As I said, this is possible in 2D and in 3D, so let's just remove those parts and bring this as a molecule into the table as well. Doesn't make any interaction, of course, but now I have 2 fragments which are in different parts of the binding site. If I select both of them and say bring them to the inspirator mode, I have them both in there together. And now I can do the same as I did before with the recore. I can select this bond and let's say this bond and get them merged together or linked together again by a recore search in here. I guess I've selected not the smartest two molecules here, but let's try what happens. Okay. Let's browse those results. Again, you can click on them and you see in the 3D how the molecules were linked together. Here this is surprising. Still found an interaction, but again, you've moved the molecule around a lot, so you get here some big red coronas in the middle. Might not be the best idea, but this was just to showcase you how this is done. This looks actually quite nice. How you can link them together with a nice heterocycle here. Might be a new idea to try for you. Okay, so I think I've covered most of it. What's new, by the way, is when you right-click here on the molecule, then you can copy the 2D depiction as an SD file or SVG or PNG. This is again nice to prepare your reports. I think one thing I've missed so far is when you create a lot of new molecules, you might want to dock them. And for docking, you normally use the standard, but you can equally bring over a little, or let's say we go over back to the proteins table and bring our crystallized molecule to the docking mode. Then you can select this as a template and run a template-based docking. This is very helpful if you just make small changes on a molecule but know that you left in your strong binding motif. When you start a template-based docking, then the maximum common substructure between your starting point, so your reference, and the new molecule will be calculated. And the docking will place the new molecule on top of the old molecule and just kind of dock the newly added bits of your new molecule. So if I select the radio button here on top, then you see this button was activated. I just deactivate this here on the button again. So you see the normal docking is now activated. When I select the template docking is activated. And when I run this, then my new molecule will be put on top of this, and I get here another docking solution. And you see now the beta-resorcylic acid still stays in place from where my original structure laid in the crystal structure. And you see only the new bits are wiggled around and docked inside the binding site. So this is a quite new feature, which is very helpful if you start with the fragment growing, for example, or when you have a very, let's say, shallow SAR where you just have modifications on one side of the molecule and don't want to throw away the knowledge you have already from the crystal structure. I've showed nearly everything. I've just realized that I haven't showed you one little switch. On the tables where you have molecules, you have a switch here on top, which switches between the table view you have now and the grid, where you see all the structures in 2D directly, and you see they have little radar plots here. If I hover over it, the radar plots get bigger, and I can actually set the radar plots differently by clicking on the settings wheel here, and you see that you can put different values on the axis. Let's say I'm only interested in molecules between 200 and 500, but the parts that really interest me are between, let's say, 380 and 480 for any reason, I don't know. Log P, okay, I'm not interested at all in compounds that have a log P of -5. I just want to have the scale until -1. Oops, -1. But interested I'm only in those between 3 and -1 because I want to have something soluble. And equally you can add other parameters, like let's say the number of H bonds. I don't want to have something with 0 H bonds, so I've put this on let's say 3 to 5. And you can add more and more parameters like number of rings. I don't know, you want something which has at least a ring. And when you apply this, it will be updated for all those compounds you have here. And you see now the green area is showing you quite quickly how good the molecule fits into your desired values. Some of the molecules here have red dots, so means like the value of this property is over the range you like. So for example, here this has a higher molecular weight than what I was originally interested in. So when you have a perfect molecule, you have a big, huge green area, which is perfectly filling out the areas that you wanted. This helps you quite good when you have a lot of molecules and want to find out which ones are the one of further interest for you. I think I've showed nearly everything. Marcus, do you give me a hint if I forgot on anything?
No, I think we're pretty okay. There are a few questions that we can discuss which have dropped in already, but these are more general questions.
Okay.
So,
In this case,
yeah,
I
if
will.
people would like to ask anything or comment anything, just type it in the chat box and we can cover this in due course.